Hello everyone, a very warm welcome to MTT-S Day 2 of Epsilon 2024. I'm Arya Jadhav, the media head at IEEE SIS GST, and it's great to have you all back for another exciting day. If you were blown away by yesterday's session on LiDAR by Mr. Saurabh Kumar, you are in for a real treat today. Also, a very happy Engineers Day to all the brilliant minds here. Let's continue celebrating innovation and creativity as we dive into today's session.
And I'm Rohan Ramakrishnan, the PR and admin head at IEEE SISGST. And if you thought yesterday's session was impressive, buckle up because today we are going to have a hands-on session with ladder technology. If you missed the first session of Tech on Wheels, no worries because you can always catch the recording later on. But what I have to say is Saurabh really set the stage for what LiDAR can do in autonomous vehicles. He has covered everything from how it maps the surroundings um, to its role in making sure the future of the self-driving car doesn't confuse a lamppost with a pedestrian. And we all agree that it is pretty important.
Exactly. And now it's time to take all the theory and put it into practice. Today's session is going to be interactive. So be ready to roll up your sleeves and dive into the real world applications of LiDAR in autonomous vehicles.
And who better to guide us through than Mr. Aditya Jagani, a specialist in autonomous vehicle technology and LiDAR systems. He is the kind of guy who could probably use LiDAR to find his lost keys in a dark room. So, yeah, we are in good hands.
Today's workshop will last about 90 minutes and we've got a little something extra in store, a quiz at the end. We'll drop the link in the chat, so make sure you're paying attention.
And without any further delay, let's welcome our speaker, Mr. Aditya Jagani. We are so excited to have you here today. The floor is yours, or I should say, the ladder mapping is yours.
Thank you for the introduction, Rohan and Arya, and thank you very much for having me. Very excited to be here speaking about LiDAR point clouds and workflows. So let's get started on how these things or how these technologies are used in the current world. Um, Before we get started, I'd just like to introduce myself a little bit. So I'm currently a robotics software developer at MathWorks, where I'm currently working with the sensor fusion and the tracking toolbox team to basically develop software for localization and perception for like self-driving vehicles mostly. And in the past, I've also worked with this new startup um, called ICAI, and it's essentially a startup from that was born from MIT, where what they were trying to do is they were trying to retrofit a truck and with like sensors and whatnot, and they were trying to carry or move containers from one place to another using like driverless tech and whatnot. So that was pretty exciting to be a part of. And I did my grad studies at WPI, which is a university in Massachusetts. And I also worked as like a researcher over there, where I was working on some really cool robots. So yeah, excited to be here talking about LiDAR stuff and the new technology. We can go over the agenda today. I'll first introduce a little bit about LiDAR, talk a little bit about point clouds, and how we can do perception with point clouds. And then we'll move on to the demo and we'll actually start doing some stuff. All right. So just to give, I'm pretty sure you must have gotten like a brief overview of how LiDAR works, but let me just quickly go over that. The whole principle of this LiDAR is essentially it throws light, right? It will shoot like these rays or these things called lasers. And since they travel at the speed of light and every surface has a particular reflectance, right? If a laser points in you, you get like radiated and some light gets reflected onto you. Um, LiDARs work very similar. They shoot out these laser pulses, and the return pulses that come from the objects, uh, the time between when it was sent and when it was received as notice. And using the time of flight calculation, speed equal to distance upon time, you can basically measure a particular location of a target. Now, if you do these things a lot of times, right, if you threw multiple lasers in the world at multiple times throughout, you can get something like this. The image, this thing is called like a point cloud, which is nothing but a set of data points in 3D. So it looks pretty cool. It's sort of like a little bit noisy, but that really depends on the kind of lidar you use and the tech the lidar company uses. But yeah, we get something like this, and it looks very very cool. There are a lot of lidar scanners available in the market. You can have one on your iPhone. The iPhone 15 Pro, I think, has one. It uses a similar principle that we just talked about. And then there are like more sophisticated or expensive lidars that use some really amazing technology to recreate that world that we see in 3D. And they are like literally the size of a hockey puck, which is really really useful for like robotic applications and everything. So this is what LiDAR scanners look. They rotate a little bit. They have some resolution in azimuth, and they have some elevation. And yeah, essentially they throw light, they capture it, and try to get a good awareness of the world around it. Over here on the left, we have a sample scan from the LiDAR, which is generated by like an airborne instrument. And then we have on the right something of like a maybe like a driverless car or like a driverless truck that went through a street and sort of recorded the point cloud of the whole city it went through. So these are some sample scans from the LiDAR. And I have with me a real-time LiDAR scan that was put onto a vehicle in San Francisco, and it's moving through the street. And you can see it got like all these rays around it, and you can basically try to, like if you see it closely, you can try to make out that over here we have a pedestrian, or there we have a car, or there we have I don't know, like a road or something like that. So it's really exciting to get this kind of an input that we can further use and process it a little bit, do some math over it, and try to make more sense of the world so that we can um, make these difficult problems of self-driving in unknown environments or even in known environments, but very dynamic, right? Very safe for other people and for basically everybody. So yeah, looks pretty cool. I'm pretty excited by this fact. Now, this is not the only way you can get like a depth map. The previous video that we saw, it was mainly capturing like depth information, right? So there are like alternative ways where you can do some other math. If you have something called a stereo camera, which is nothing but if you have two cameras, which is separated by a distance called the baseline. So we over here we have like a really nice camera from Stereo Labs called the Z camera, and it can essentially uh, do some math, triangulate some distance, and try to find out what the distance of the object is. Um, and over here, I have a pretty cool image that came from something like this, where you use a stereo camera to detect depth of an image, and this camera is mounted on a vehicle. So the yellow, like the more yellow pixels, I think they are like the more closer to you, and then I think the lighter ones or the darker ones are like more further away from you. So this is like essentially the raw output that you can get from lidar or depth camera. So once we have the depth information, we can do more stuff with it, right? So let's see how we can do that stuff in theory, or the the libraries or the tools that a robotics engineer uses, um, I'll just talk a little bit about that. So there's this like really amazing framework called the Point Cloud Library. It's got certain APIs, it got certain algorithms already built for you so that you can just, you know, plug some things, feed some data into the sensor and try to play with it, get some output, feed that thing into something else, and basically make your own custom little application. So this is something called as the PCL, as it's commonly referred to, Point Cloud Library, where you have a certain image, and based on that image, it can also create this depth view. You can visualize it, and it can also identify the key points that you would be interested in from the whole image that you can, you know, use further to do some other exciting stuff. And then there's this another amazing library. It's called Open3D, where you can visualize a lot of these point clouds. So these are, I think, like very like famous or very widely used libraries in my world, I think. And yeah, you can use them. And since I work at MathWorks, I'll probably bring this up. MATLAB has a LiDAR toolbox where you can do very similar things very easily, and it's like not complicated. You don't need to install anything. You can just use the MATLAB software, have the LiDAR toolbox, and then you can upload point cloud data. You can view it. You can probably pre-process it, play around with it, like using like a GUI like this, or you can code your way and make like really amazing applications, right? So as I mentioned, let's talk about once we get that depth data, right? How do we sort of process it? Can we use it directly? Is there like particular steps to basically using it? So yeah, I'm gonna basically talk about a few of these pre-processing steps that we need. So the first one is the denoise, right? So these sensors, as you mentioned in the one of the previous slides, it was quite noisy, right? All the points were moving quite a bit, and we don't want those points to move when we put that kind of a sensor on a car or like a self-driving car, because we don't want that uncertainty in our image understanding or the world understanding, if I may. So we need to sort of remove these noise or outliers from the 3D point cloud. Um, and on the right over here, we see like once we apply that operation of denoise, we can get a much cleaner point cloud, which much fewer, um, less noise essentially. Another one is downsample. Downsample 3D point cloud is the issue with point cloud is there are a lot of points, and if you want to compute everything in real time, it becomes really challenging for you to basically compute. So I think in this particular image there might be like 65,000 points, which is a lot, right? 65,000 points of XYZ locations in your plane, and that's only for like one thing. On self-driving vehicles, you can have a lot of a lot of points, like it's like a 360, right? So in order to process so much information at once and make this algorithm output whatever it is doing in real time, it's very difficult, right? Because algorithm takes some time to process. So we need this downsample 3D point cloud to essentially remove a certain point in the point cloud such that we still have a good understanding of the world, but we are at the same time able to, you know, output real time performance, or yeah, process everything in like almost real time. This is optional. If you have a really amazing GPU, then maybe don't do it, right? And one more step is something called as ground plane removal. You remove the whole ground plane from this. There are a lot of points that we see in um, the whole self-driving scenario that we saw, real-time lidar scans, that there were a few points that were coming on the ground. Sometimes we don't need those points so that we can at least identify the objects that are present in the environment. So we try to sort of remove the ground plane so that we can see that, okay, we have a lamppost, we have a tree, we have maybe a pedestrians or something like that, and the scene gets like more cleaner, and we can process like really fast. And this one I think is called the ego motion compensation. This one is essentially a step that's very closely related to when you put lidars on moving objects or moving platforms. One lidar scan, around like a 360 scan, it takes certain time, right? If your vehicle moves like really fast, that one rotation can have distorting effects on the point cloud that's created. So when you go at like whopping speeds, right, and have a lidar, it's not going to create a really like nice point cloud for you. So you need to sort of account for that motion in your platform or your robot or a car, so that you can sort of say that, okay, I scanned my environment at t equal to 1, right, and I'm currently at t equal to 1.2 seconds. So I need to sort of account for that zero point 0.2 seconds, the point clouds I got at zero point 0.2 seconds, to sort of defer back to the original point cloud time, which was t equal to 1. So something like this. So yeah, we need to like undistort the point cloud that's affected by ego motion. And there's one more step, which is the segmentation, which is nothing but grouping of the point clouds, right? If you have two point clouds like this, one you have like an inner circle and then when you have an outer circle, then you could probably apply some math. You could probably apply some algorithms, right? Euclidean distance or something like that, maybe, and get two things, right, like two groups, that okay, these set of point clouds belong to one group and the other ones belong to the other, right? So something like this, it really helps in like pre-processing. And I think um, these are like basically the founding steps to do like object detection or like lane detection, or I don't know, whatever you want to do, right? So now we'll look at whatever you want to do. So the few things that come on the top of my mind is, once we are able to clean that raw data, now we can start having to perceive the environment. The perceived environment is not just like see the environment, but make sense of it. So you can detect objects once all these pre-processing steps are done. You can localize, meaning you can find your own position in the entire world, um, using these lidar techniques. And you can also probably like build a really nice map of your city if you have a lidar scanner. Uh, One insight I would like to share is, I recently went to like San Francisco, and they have these like Google Waymo cars, right? And they have like lidars on the top, and there are several other companies also doing this. But they first try to like build a map of like the San Francisco city where they want to like operate, and then they start like basically navigating it so that it's more like, okay, I've been to this place once, so I think I know where I'm going at or how things are looking. So the car is like more certain of the things it does, and it's essentially could be like more safe as well. So um, building a map is important for like these robot taxi companies at least. So the first one is object detection. The segmentation step that we saw, right? That we first like remove the ground plane, and then we just get these objects, um, all the unwanted points in the point cloud like eliminated, and we just keep the points that we want to keep. Once we do that, maybe we can apply some kind of like math to detect, okay, here's an object, or here's a particular thing. Maybe apply deep learning models to detect these objects. So on the right here, we have like a really big point cloud of a car at an intersection, and you have multiple parked and non-parked vehicles also. And once you do all these pre-processing steps and segmentation and clusterize these points into groups, you can very easily sort of detect these objects around you, right? And just a little bit about how you can build a map. um, it's a really, really interesting and really intriguing process of how you can do this. There's a technique called registration, which is you register two point clouds, right? You have the first point cloud and you have the second point cloud. If you try to find a relation between the first point cloud and the second point cloud, saying what's my rotation and what's my translation that I can apply to my first point cloud, that it becomes my second point cloud. If you have a LiDAR mounted on your vehicle, you can essentially know using this registration technique about rotation and translation, the change in the relative rotation and translation, that how much your vehicle moved, right? So you have a point cloud one, point cloud two, you know the rotation and translation, you you move forward and you somehow have localized your vehicle, and you have a better understanding of where your vehicle is. So doing this incrementally, you can essentially build a map that we saw in one of our previous slides. So really exciting uh, things here. Very simple maths, but very impactful, um, very useful as well. All right, so I'll stop yapping about and giving presentations, but actually, let's move on to the real stuff that you want to see, which is point clouds and all the things that we discussed right now. All right, all right. I'm hoping you are able to see the screen. So I have a script with me that I've written, which will go over maybe line by line and try to get a maybe like a just basically talk about um, the things that we just talked about in the presentation. All right, so this is MATLAB, and I have the LiDAR toolbox installed on my computer. And we have just loaded all the point clouds and all the data that we need. This is some real-time data that we have captured. And we'll start by first visualizing this point cloud, right? So we first retrieve this particular point cloud. I have just picked the first one. And then I use this function to basically create a figure and show this particular point cloud. Right. So this is a really nice, like, so we have like a vehicle over here, and it's got a LiDAR, and then we can see like a really nice point cloud of cars, and I think these are trees, roads, and whatnot. It's not clear at this point because there are so many points, but let's try to sort of reduce these points and make more sense of it. But this looks really cool. Every point has a particular intensity. Every particular point has a particular color. The color is decided on how far that particular point is in azimuth and elevation, which is like up and down, like horizontal field of view. And according to that, the whole point cloud is created. So very nice. So we have like 500 point clouds. Let's try to quickly visualize this particular point cloud, right? Just get a better understanding of the world or what we are seeing from this real-time scan. So we can see there's a vehicle that's turning at this intersection, and it went quite fast. Um, I have just put like the first 100 points to view, but yeah, gives you a good understanding of our data, right? So let's move on to the first pre-processing step that we need, which is how to eliminate the noise. We don't want any of the noise, right? So MATLAB provides you really simple APIs that I previously mentioned in the point cloud library, right? That you get these APIs, you get like all the work done for you. So you just get the function name, the method name, provide the point cloud, and provide maybe some arguments, input arguments that are native to that particular function, tune it a little bit, and see what works for you. So MATLAB has something called as PC denoise, which is point cloud denoise, where it can eliminate the noise for you. Over here in this particular figure, I have um, two point clouds sort of like overlapped with each other, where the green point cloud is the denoised point cloud, and the pink point cloud or the magenta is the original point cloud. And we can see that these are like probably like noise, or these are like really sparse points, 3D points that we probably don't want, or we probably are not interested. And essentially, we can like sort of get rid of some of these point clouds and get rid of noise. Um, I I'm not sure if you can see it, but I do see there are a lot of these unwanted or like noisy points in like this direction. So um, yeah, if you can't, just assume that we have successfully removed noise from this point cloud, right? Now, the second step that I mentioned was how to downsample, or how to get rid of a lot of points so that we still have a good understanding of the world, but we are able to sort of remove a few points essentially. So MATLAB has something called as PC downsample. You provide the original point cloud, provide some kind of an input argument to it, and let's sort of visualize the original point cloud and the downsampled point cloud. All right, so on the surface, both of them look like really similar to each other, but let's try to zoom in a little bit and we'll find out what this particular function did for us. Right, so on the left, what I'm zooming is the original point cloud, and on the right, let's zoom in at the same point, and we can see that there are much less points now. It seems that I might have downsampled this point cloud a bit too much, uh, but you can sort of, tune these values so that you can hit your good spot, right? Keep what you need, don't keep what you don't need. So yeah, this is how we can downsample these point cloud. The third step is to remove this ground plane. Let's try to run this section. MATLAB has something called as the segment ground from LiDAR data, which is nothing but like a function name, where it will it will sort of give you, um, how do I say this? It will sort of clusterize the non-ground points, and it will clusterize the ground points. So it, this is like a difference thing, right? You can see that you're able to correctly identify most of these ground points in magenta, and most of the non-ground points, which are z greater than 0, like z-axis greater than 0, in green, right? So you can get you're basically able to like get rid of the ground. So we have the original point cloud, and then we have most of this ground points removed. If you noticed in the video that we saw earlier in MATLAB, that there was some sort of like a bump when the car was moving, and that's why the whole point cloud sort of like shifted up. um, I'm pretty sure these are the points from that bump, right? So maybe add some more pre-processing on these steps and try to uh, see your point cloud or see your data like step by step, and see what makes the most sense for you and works for you. But yeah, looks pretty cool. And moving on to the next step, which is uh, let's see, what do I got? Segmentation. So this is what we talked about, right? How can you, once you are getting rid of the whole ground points, now you are moving closer to making sense of the world. That what are my objects in this particular scenario? How do I club them together? How do I know that out of the 65,000 points, point 1 and point 10 are belonging to the same object or not, right? So we need to learn about all these. So using some clever math, using some segmentation techniques, they work on finding the distance from your neighbor points to your point. I don't know if that made sense, but um, essentially the whole idea is nearby points stick together, and once you are able to segment the whole image, you can make you can basically assign mm, groups to a set of points that belong to a particular location. So over here we see we have a like a car that's noted in green, which is like all these points are together. Then I think we have a tree over here, which is also of a different color, meaning we have successfully identified all the points that are belonging to that particular tree. And I guess we have like one more vehicle over here where all the points are marked in like yellow. But you can also see that this particular algorithm has incorrectly identified some of the ground points that are located or that are belonging to this particular object, right? So nothing's it's this is actually a real world scenario where theory, and there's a little bit of a difference between theory and practice. uh, this is like a real world sample where once you ideally you would like segment and you would get to know, okay, here's an object, here's an object, object one, object two, whatever. But in real life that sometimes does not happen, and sometimes it's most of the time. So you need to like make sure your algorithms are doing all the proper math and everything. um, the MATLAB has like, you can provide some input arguments, you can play around with this particular thing, visualize your data and make it like cater to your needs, as I mentioned before. All right, so now we have pretty much covered all the basics of pre-processing, um, downsampling, clustering, removing ground points, and whatnot. Now we will move on to the idea of how we can essentially create a map, right? The thing that I mentioned about trying to localize yourself, localize a vehicle, given that you have two point cloud one and two. If you know the rotation and the translation between these two point clouds, you can know how much your vehicle moved in that time. So let's look at some of the basics or some of the um, I don't know, like yeah, the fundamentals of how you can build a map. So we'll do that with like just 2 point clouds for now, and then we'll move on to a really heavy example after this. But all right, in this line, I have a teapot, a point cloud of a teapot. It's a PLY file. There can be PCD files. There can be, I think there are like a few extensions that you can use for point clouds, but I think PLY and PCD is like the most that I've used. Right. Um, let's see if we can try to visualize this. All right. So we have a nice little point cloud of a teapot that somebody created for us. Right. Now, what I want to do is I want to rotate this particular teapot with maybe like 30 degrees in the Z direction and move it a few meters around. So in like XYZ. And I sort of give it the transform, which is essentially like a homogeneous matrix consisting of rotation and translation. And I try to like basically move this particular point cloud, rotate it so that now it looks something like this. This one's the original one. Oh, sorry. This one's the original one on the right, where it's facing the right way. And then you have on the left, which is sort of moved a little bit, 60 degrees or 30 degrees. And even in XYZ, it's moved um, accordingly, right? Now, what I want to convey is how you can relate the original teapot with the transformed teapot such that you can try to find the homogeneous matrix that relates both these point clouds. So this is a really interesting algorithm called ICP, iterative closest point, that tries to take these two teapots and somehow like try to like match it based on some minimum distance or minimum weight or something like that, right? And it tries to essentially minimize the distance or get the most like accurate overlapping of both these T points, and it actually gives you, so once I run this, it actually gives me the registered point cloud of um, so I have the transform teapot here. I apply the ICP registration algorithm on this, and it gets to know that okay, if I rotate um, my my transform teapot in minus 30 degrees, maybe move it a little bit over here and there, I am able to sort of rotate this image to get this image, which is the image over here, which is the registered point cloud. Uh, Hopefully that made sense, but let me see if I can make it more clearer. Right. I have um, the transform that I obtained from this particular PC register ICP algorithm method. This is giving me what my rotation should be so that my transform point cloud is able to like when I apply this transformation to my second point cloud, I can get my original point cloud. And these are the transformations associated with it, where I can see that my original transformation looks something like this, where I had a few elements in the rotation, like the R matrix, and then I have like 5, 12, and 10, 5, 12, and 10 in the translation. And after ICP, I'm able to get almost very close values to the original ones. And that's how I know that I have minimized my distance between these two point clouds. And I have a very, very accurate um, transformation between two point clouds. So this is essentially sort of like the base of how you can localize a vehicle, right? So I hope you understood this part. I apologize if I wasn't clear, but I really hope you understood this so that we can move on to the next uh, exercise, which is how you can build a whole map from just LiDAR data using something called as SLAM. SLAM is simultaneous localization and mapping. Localization meaning just what we did here, right? Get the transformation and rotation and translation between two point clouds. And once we are able to get that rotation, uh, the point cloud that we got at the second time step, sort of add it to the current existing point cloud, right? Then we move a little bit ahead, and then we get some point cloud and then add that point cloud given the rotation and translation uh, in the world. And that's how you can like sort of incrementally build the whole map. So it's pretty exciting. Let's sort of dive deep into this. Let me just quickly load my data. Hopefully it loads very soon. Okay, I'm gonna give it a minute, but even if it doesn't happen, then that's fine because we have everything we need. So yeah, let's just give it a minute maybe. So sometimes these things like take a lot of time when you have like recorded data with you, because these point clouds, like each point cloud from a driving scenario data, um, I think if we just check out like one of these point clouds, it might have like 60, as many as 65,000 points. And if you, the sampling rate of a LiDAR is, I think somewhere around like 20 hertz, or good LiDARs, maybe like 30, 40 hertz or something around that. So it means there are like 65,000 points times 20 times the number of points, or the resolution that you have. So it's a really like bunch load of data with you. Um, so retrieving that sometimes takes time, but I think we can move on to the next, basically what I want to convey. All right, so over here, how we can build a map from point cloud data is numerous ways. We can either just apply the um, oh, there we go. It got loaded. Um, we can just apply the ICP algorithm, right? And try to build on the map. Or we can maybe make things interesting and add another sensor. If you, it's called the IMU, Inertial Measurement Unit. It tells you how much acceleration, how much velocity I have, like my vehicle has, and maybe try to fuse the values that we obtain from the registration algorithm by associating two LiDAR point clouds and the IMU data, which gives us the rotation, velocity, acceleration, and whatnot. And basically try to fuse this data and create a really accurate map, because sometimes point clouds, they don't work well when your vehicle is rotating. It's good for associating two like translated point clouds, but sometimes, and this might happen, that your vehicle is sort of moving at the intersection at like crazy speeds, and it's not able to correctly sort of minimize the distance between those two point clouds. That happens a lot, and that might result in poorer maps. And yeah, so you don't want that. You want your maps to be really nice, looking really nice. So um, we can use like an IMU sensor to fuse those values and make sure that your maps are good. All right. So on this line, I'm reading a particular point cloud in MATLAB, where I have the first point cloud that I'm reading, and I'm trying to display what that point cloud contains. So the point cloud is of the point cloud object in MATLAB, and this object has a structure. It's got a location of all the points. Those are, it's a matrix of 64 cross 870, which I'm guessing is the horizontal and the vertical like resolution. And it's got the XYZ points for all those particular like points. And the total count is like 55,680. That's a lot of points. And yeah, we got some information with the point cloud. Now let's look at what the IMU information holds. The IMU information holds the time at which that IMU came, the heading, pitch, roll, and the XYZ angular velocities, essentially, right? So, also, one more thing that I would just like to add is LiDARs, they operate at like maybe like, as I mentioned, 20 hertz, but IMU operates at very fast, like it's like 200 hertz or 400 hertz. So in one reading of LiDAR, you can have as many as like 50 like measurements from the IMU. So you need to somehow like create that correlation and make sure that you're fusing these measurements at the correct time step. Otherwise, everything is going to like mess up. The whole map is going to look like, I don't know, like a kid made a drawing or something. Um, so you need to make sure that the math works. Um, so let's try to see if we can visualize this point cloud. All right, we'll just take a minute, um, see if it loads, but it should mostly. But essentially, this is like very similar. This point cloud data is like very similar to what we saw in the demo script of the whole like visualization. So nothing new over there. But let's go over at least the steps on how we can build a map from using like LiDAR and then IMU. All right, so we'll go step by step. So I'm first creating these pre-processing parameters of how much I want my point cloud to be downsampled, which is like maybe like 10%, 0.1. And then how much I want like my grid size to be, which is used in my registration algorithm. So essentially, just high level, we initialize some parameters for the algorithms that we are going to use in the bottom. Then we create two variables, which are the transformations, rotations, and translations. One is called the absolute, which is going to give you the world coordinates, everything in world coordinates. And the other one is called relative, which is how much did I move from my previous time step to my next, like my current time step, right? So we are going to set it as like all like identity matrix for now. And then um, we have some display parameters, and we basically loop over these frames and read the first point cloud. When we get this particular first point cloud over here, we pre-process it and sort of remove some noise in that's present in this like helper function. So we essentially remove this particular noise, and we are able to like segment the whole point cloud into two things, where we are first removing the whole ground plane as we talked about. And a lot of these times what happens is when you have a LiDAR mounted on top of a vehicle, and it's got like a really nice like a steep um, elevation angles, some like the hood of your car will be showing up in the point cloud, the rear of your like vehicle would be showing up in the point cloud. So you need to make sure that you're removing all these points, right? Okay, there we go. I told you it would work. But yeah, this is essentially the data that we are trying to build the map for. It's approaching these intersections and coming back to the same place, stopping at these intersections. These are all like various scenarios, right? Like your vehicle is moving, your vehicle is not moving. Some of these sensors have uh, a really strong suit when like things are moving, but they don't work very well when things are not moving, like the platform is not moving. While other sensors, they are like very good at um, measuring things when everything's like static. So you somehow need to like account all of this like uncertainty into when you're like trying to design these algorithms. But yeah, we saw like a really like nice data set that we are working with. All right, and coming back to what I was talking about, which was we first need to remove the ground plane, and you also need to remove the points that fall on our vehicle, so that we are only capturing the points present um, in the world that we are interested in. So we got that point cloud, and then we first downsample it using this downsample percent, which was set to 0.1. And next, we in this particular like loop, what we're doing is if it's the first frame, then um, uh, like add view is nothing but um, in the end we want to visualize the whole map, right? So it's just like this whole short like code snippet designed to store the point cloud, the relative transformation, the absolute transformation, and the point cloud that was associated with. This will come in handy later, but yeah, the more important thing is once we have the point cloud, we will try to get more information from the onboard IMU that's present on our vehicle. And this particular helper function tells us what is my transformation between the two LiDAR scans that I got, right? So if we, I think, go here on top, we can see that um, we have the INS data table, and we have like 2,500 sample points. And I think if we try to see how many point clouds we have, we have probably probably the same amount. Okay. All right. So coming back to this step, which is right in a T form. This is the estimation or the transformation that we obtain from our IMU. What it has is at this particular time step, we have the homogeneous matrix uh, that that contains some information about how much we moved in translation and how much we sort of rotated, right? Does not seem like we rotated. We only seem to have gotten like 0.032 like ahead in like X and Y, and then moved a little bit inside. This is only at the first time step. Now let's go on to the next step, which is we update the absolute transformation that we had first initially set to identity and multiplied with this new relative transformation that we got, so that we know how much did our vehicle move in the world with respect to the original one from where we started, right? So it says absolute transformation to the reference frame, which is the first point cloud instance that we got. We add these values in at what time did we notice it, what was the initial transformation at that, and then what was the point cloud that we obtained at that particular time step, so that we can like basically visualize everything. And then um, okay, I might have missed one step, but let me quickly go over everything. So it's like you first read a point cloud, then you segment it into ground, non-ground planes and um, I don't know, points that don't belong to your vehicle, you sort of get rid of that. Then you downsample it so that it's faster for processing. Then you get the initial transformations from the IMU, right? How much you moved. And then we also need another set of these transformations that we get from the LiDAR, which is the PC register NDT. This is very similar to the PC register ICP that we saw in the previous example. So what it does is it tries to find out the relation between our current point cloud and our previous point cloud, and given some input parameters, we can try to find out what the relative transformation is. So so the relative transformation that's coming from the LiDAR, the relative transformation that's coming from the IMU. You sort of feed this initial transformation from the IMU into the LiDAR so that it has a good estimate on where my point cloud, or what the rotation or what the relationship between my two point cloud would be, right? So that it's faster to sort of minimize it. I can still minimize it without the IMU, given that I have like two point clouds which are like really far away, but it might take a lot of like iterations, like 500,000 iterations to sort of minimize that distance. But if somebody told you, hey, I think I know I moved like so much and so much in X direction or Y direction or something like that, then that initial estimation or that initial transformation or guess really helps you, or really helps this algorithm become like more fast, and you can sort of associate the relation between these two point clouds, right? And that was pretty much the whole gist of how you can build a map. That you get the relative transformations from the registration algorithm, you multiply that with the current absolute transformation that you have here. So this will give you how much I moved from the previous time step. And then you get one more, like at the next time step, you get one more relative transformation, multiply that with the absolute transformation. And so on and on, you can sort of try to incrementally localize yourself, that what my position is. And based on that localization, you can also insert these point clouds, right, in those locations. And that's called mapping, where you create the 3D map. And that's essentially what SLAM means, that you simultaneously localize yourself and you also map your surroundings. So yeah, that's pretty much the gist of it. Let's see if this thing runs. And I could probably show you like a nice map that's getting built from uh, this particular data that we saw, and if this loop is working or not. So over here we have these points in like X, Y, and Z. Seems like and it gets updated at some time, so it's not real time. uh, but we can see that the vehicle was moving at some intersections. It uh, went and took some paths, took some ways, and we can get like a nice like trajectory of the whole vehicle, given the data from the point cloud and the data from the IMU. And essentially, I think we would be able to. So this was the localization part of it, where we were able to track the trajectory. Now, if you want to sort of do the SLAM, which is visualize the uh, trajectory as well as the map at each instance that it made, it looks something like this, where we have like an RGB map, and then over here we also have like the red trajectory of the vehicle that it took. And I guess we might be able to visualize the whole map. There we go. So it moved apparently, I think like maybe like 250, 350 meters in this direction, and maybe like, I don't know, 350 meters. So it moved a lot. And then we get this like really nice, amazing data in X, Y, and Z of the whole point cloud where the vehicle moved. Seems like a really like nice highway some way. And you got like all these trees, you got all these roads, you can dive into this particular data, and you can sort of like visualize every single thing what the vehicle saw on its way. And looks like you don't have any looks like it's like a continuous map. It's not broken at any points. We were able to correctly register incrementally the map, and in my opinion it looks super. So yeah, I think that is pretty much what I wanted to do for demo. um, the map, the slam, right? And just a few things I can talk about is the applications of like what we just saw, which is like object detection, localization, mapping, lidar like scanners, whatnot. Very useful for like uh, self-driving tech, but also for like not self-driving tech. You can use it in like for like driver assistance, maybe in like remote sensing to sense um, the bed, the seabed, and see what's like underneath. You cannot see a lot of stuff below the ocean, so you can use like lidars over there. You can use lidars in self-driving tech. You can also use lidars for like completely like autonomous driving, create maps, high definition maps, and so on and on. So just to sort of like go over and conclude this presentation, the key takeaways of this is point clouds or depth map can give you a very good estimation of depth. And once you have that depth, you can basically do anything with it. You can pre-process it, process it, do slam, build a map, navigate yourself using all these third-party libraries, PCL, Open3D, MATLAB. Very useful. So yeah, I guess this might be it from me. So thanks very much. You have been an amazing crowd. Um, I am Aditya Jagani. Feel free to collaborate on LinkedIn. I myself work on a lot of these self-driving projects that I'm working on. Um, so if you're interested in something like this, making a really big robot, coding some amazing tech, uh, please feel free to like reach out to me, and we can talk further. But thanks again for being an amazing crowd. Thanks, guys.
Yeah, wow, that was a really amazing hands-on session. Like, really, really learned a lot about how to build maps using Slam and those amazing data sets and really cool maps. And also, like the thing you said about point cloud, clustered point clouds, and segmentation. So, really, thank you so much, Aditya, for walking us through the LiDAR technology.
Absolutely. I think everyone has a much clearer picture on how LiDAR is shaping the future of autonomous driving. Now let's open it up for Q&A. Drop your questions in the comment section and we'll get them answered.
Yeah, and don't be shy. This is your chance to get those burning LiDAR questions, right?
Yeah, please feel free to like shoot out any questions you have. It can be any silly question. I don't really care. I was a recent like grad student, so yeah, don't be shy. Oh, okay. We have one question from Shreyas. He says, "What are the trade-offs between different lidar sensor types, mechanical versus solid state, for use in like real-world applications?" Yeah, Shreyas, that's an amazing question. It actually, so solid state lidar sensors, they work on like a different kind of tech and different kind of like wavelengths, and mechanical lidars, they work on something like a different tech. So it really um, it really like depends on the application that you're trying to do or that you're trying to work with. Um, but as for the trade-offs that I can think, I see that there's a difference in like resolution, there's a difference in speed, there's a difference in the depth of this like point cloud, and yeah, I think that's what I can like think for. Does that answer your question? All right, we have one more question from Krishti. It says, can you share some real-world challenges you face when deploying LiDAR systems in dynamic environments like ports or city streets? Yeah, absolutely. I have worked on mostly like recorded lidar data because that's what like robotics engineer do. um, Most of them don't go out in the field, they like sit at their home and try to their office and try to code everything. But the real world challenges would be, I guess, um, there are these few like edge cases or few points that you cannot like really see. Some of these objects in this environment, they're not like reflected back, right? So few of these things, since you're not able to see, or there are few things that you cannot make out of the lidar, you need some additional like sensors to sort of have a better understanding of the world. And that's where like this like sensor fusion comes in, right? um, oh, it seems like we are getting a lot of questions. So Mansi says, how do you see the future of lidar and low cost autonomous systems? um, I am not sure if I'm the right person to be asking that, but um, like lidar technology has come a really long way. Earlier, if you see, these lidar sensors, they were like really expensive, like $70,000, $110,000. But now it's like become like much cheaper because of these like new companies like Ouster. They're making like some really like nice lidar, and sort of we need to like think a little bit about um, how much how much like data, like point cloud data, is like good enough data for us. Most of these lidars are pretty good. The thing or the challenges that we face is essentially more on the side of um, like algorithms and making that math work for you. It's very difficult to be working in like really high speed environments where you're going at like 60 miles an hour, which is like I think maybe like 80 or I don't know 90 kilometers per hour, right? At these fast speeds. And in such times, you need to have like a really good understanding of the world. If you're not able to like fuse your senses together, or if you are not able to like detect a few things, um, you it faces like a really like big challenge in terms of like safety to human life, and it can lead to like accidents. So which is why it's like a really big challenge to be operating at like really high speeds. But I think we got a question about ports. um, Operating at ports with lidars, they have done that kind of a thing very recently, where they're putting these self-driving trucks in ports. They come pick up the cargo, move, and since they operate at like 20 miles per hour, I think 20-30 miles per hour, um, they are like relatively safe. And in those areas mostly there are like not many humans, so it's relatively like safer to be operating at lower speeds, so that you can get like more time to react, more time to see, more time to process, right? So Tejas says, how do you manage the balance between LiDAR data resolution, processing power, and real-time systems? Yeah, that's a great question, Tejas. That's actually one of the challenges that we ponder a lot about. There are these embedded machines, there are these GPU accelerated devices. These NVIDIA is making quite a lot of them. So how much ever your system can handle, it's sort of, um, I guess, it's more like a design question that based on what your application is, you will select a computer that is able to process things like really fast and just try to like measure the runtime performance of some algorithm or of your whole application and whether it's able to actually run in almost real time on your like embedded computer. All right. So somebody says it's a if a self-driving car is faced with a potential accident, how should it decide who or what to prioritize for safety? Um, I think the way that we work is we usually give safety to like almost like literally everything. There have been like edge cases, especially in like the port scenarios. I don't know, like I think port scenarios are really nice example for this. That sometimes near the sea, you have these seagulls or like pigeons stand on the road or the tarmac, and wherever these self-driving vehicles or like this autonomous trucks are working, they will like basically stop for that seagull or that pigeon and try to not cause it harm. Um, so it's really more the issue is more at like how you want your behavior of your system to be, and um, yeah, it's essentially like how you want your system to run. If you want to cause harm, you can cause harm. If you want to make everything safe, you can do that. So there are like different applications. Defense has some other priorities. Self-driving tech working in cities where there are like a lot of people, um, safety is of utmost importance. Human life is like very important. So yeah, I would say prioritize always. I think humans and living things. I guess. So Suniti says, how do you ensure accuracy and reliability of lidar-based maps in presence of dynamic obstacles and environmental challenges? Um, yeah. So nice point to hit on, Suniti. Um, the registration algorithm that we talked about, right? That you have like two point clouds and you try to like merge these things together. Now that's based on an assumption that nothing or nothing has changed in this particular environment. There wasn't like a really high speed vehicle that was like rushing past through it. Because if there was, then between two point clouds, there will be like major difference, and you might not be able to minimize that error, and you might not be able to sort of get a good correspondence between two point clouds. And now you don't have a good estimation of your rotation and your translation. So now you messed up one map. Now even after this, if you're doing some really nice like mapping or like slam and everything's working perfectly, because of that one point, you have messed up your entire map now. So this is like some of the challenges. It's like a research field, right? Everything's like ongoing. We try to come up with good math. Most best We follow like best practices for it too. Like if you want to do a map, then make sure everything's running like nice and slow and smooth, so that your computer can do the math at its own speed and build a nice map. Because it's more like a one-time thing, right? You build one map nicely and then you can just use it as long as it don't change. So yeah, really good point, Sunidhi, on the dynamic obstacles part. Shruti says, what are some advanced techniques you've employed to improve point cloud segmentation in noisy environments? Um, let's see. Um, My so I've dealt with like so my work recent work, a lot of it involves like doing like visual slam, which is like using computers. It involves lidars too, but it's mostly like using like stereo cams and like cameras to like basically map things and localize yourself. So um, about this like segmentation thing, I think one thing that I can say is deep learning is a really like nice and upcoming field that's able to give you or deal with these like noisy environments, or is able to segment a lot of stuff, detect a lot of stuff, cluster a lot of stuff for you. And I think there are like different kind of like research papers, techniques. They all have their trade-offs, advantages, disadvantages to each other, and everything really boils down to your application that you're trying to do. So I think, Shruti, I think uh, deep learning has a really big scope in um, like using deep learning for like uh, in the lidar, like processing lidar scans, point clouds, and so on. So Shalini says, how important is it to pre-process lidar data in real-time systems, and which pre-processing step is the most critical for system performance? uh, yeah, so important, as for the important, it really uh, there's no like one like important step, because if you don't have a noisy data, right, if you don't have a noisy point cloud, if you have a really expensive lidar, and they have done a great job at like making things like most accurate for you, then you probably don't need the denoise step. Right, so essentially it depends on the data that you are dealing with. um, some of this data is like really noisy, very hard to work with. But yeah, it really depends on what kind of lidar and how much touching you got. So um, yeah. So Atharva says, what advancements in lidar processing do you foresee in the next 5 years, especially with respect to autonomous driving? Not sure what advancements mean here, but um, I guess this is like an upcoming field. A lot of people have different approaches to like using lidar, or then using some other methods to create these point clouds. So as I mentioned, you have like these like depth cameras also, right? Nowadays they are becoming like quite accurate. So for low speed applications, you have these like other deep learning depth estimation algorithms that you can use, that you can put in place to very accurately like detect depth, and they actually do quite a good job of like detecting maybe like 20-40 meters. Not as good as lidars, but I guess sort of using, so no one lidar, like no one sensor is good for you for like self-driving tech, right? You need to make sure that you're getting as much information as possible. um, GPS gives you a very accurate location of where you're where you're at. These lidars, they can mess up this particular thing very easily, as I mentioned, with the dynamic obstacles and whatnot. So uh, you need to sort of uh, make get the most information and make the best out of it, and use all of that information to get the most and most accurate understanding of the world around you. So yeah, I think uh, that's it.
Okay, so all right. That brings us to the end of the Q&A, and I hope everyone got their questions answered. We would like to give you a token of gratitude. So a big thank you, Mr. Aditya, for your insightful session today. Your expertise and knowledge have been truly good for this workshop, and we are grateful for having your time and contribution. Hey, do you know what time is it now, Arya?
Yes, absolutely. It's quiz time. The link is up in the YouTube chat. Make sure you're using the knowledge you gained here by answering all of them correctly.
Yeah, and with that, we would like to wrap day two. And don't forget to fill the feedback form for day two session. And we would love to have inputs from the audience.
Thank you all for tuning in. We'll see you tomorrow for day 3, which promises to be just as exciting. Stay curious, keep learning, and remember success is like a LiDAR scan, it's all about precision.
Yeah, well said, Arya. See you all tomorrow. Thank you.
All right. Thanks, guys. See ya. Bye.
See you. Thank you.